So we have been talking about probability lately, and there is one more key thing that we're going to be looking at, which is the idea of counting, or what's sometimes called combinatorics in advanced mathematics. And while counting, like you see in the slide, looks like you're just going one, two, three, what we really care about in advanced math is counting with things that are a lot bigger than what you could do with your hand. In advanced math, counting or combinatorics means figuring out how many ways something can happen or how many possibilities there are for a given situation. You want to think like how many ways could you shuffle a deck of cards, like the example that we had yesterday in that film, or how many ways you can do almost anything else. And again, what we really care about are things where it's so big that you can't just immediately come up with that answer. We've already done a couple of ways that you can think about counting, the most important of which is what was called the fundamental theorem of counting or the multiplication rule. That was the one that said if there was one thing that happened a certain number of ways and another thing that happened another number of ways, you multiply to figure out how many ways they can happen together. And so we did examples like if you had a class of 7 boys and 8 girls, you'd take 7 times 8 and figure out there's 56 pairs of boys and girls you could select. Or if I had a penny, a nickel, a dime, and a quarter, and I wanted to figure out how many ways all of those coins would land, you'd take 2 times 2 times 2 times 2, or 2 to the fourth power, and it ends up being 16 for the answer. There was a problem in the film yesterday that was kind of like this one. It said if you had a multiple choice with 30 questions and each of them has 5 answers, how many ways could you fill the test out? In the film, they actually talked about a 100 question multiple choice test. Well, this problem, you'd end up taking 5 times 5 times 5 times 5 until you get 5 to the 30th power. And that's a huge number. 5 to the 100th is an even bigger number. And it's something that is just highly unlikely to happen with exactly the correct answers. Many of the things that we talk about with counting involve the concept of factorials. And this was also something that came up in one of those films that you looked at yesterday, but we're going to learn about it in detail today. A factorial uses the symbol exclamation point. You'll see things where it looks like 5, where you have 5 with an exclamation point after it. And that means 5 factorial. Factorial is an operation that's defined on whole numbers. You might remember that whole numbers were like 0, 1, 2, 3. They were never negative, they were never fractions. This is something that you can only do with whole numbers. Again, the symbol is always an exclamation point. There's a couple of ways you can think about factorials. Most people think of factorials as taking any whole number times all of the natural numbers less than it. So like 4 factorial is 4 times 3 times 2 times 1. You keep multiplying times all the numbers less than it until you get down to 1. And you can see here 1 factorial is 1, 2 factorial is 2, 3 factorial is 3 times 2 times 1, which is 6. You could do that with any number factorial. If I wanted to take 10 factorial, it would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You keep multiplying until you get down to 1. So on the screen there, you can see 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, the official definition of factorial looks a little bit different than that. What it says is that 0 factorial is 1. It's just defined to be 1. And if you have any number bigger than 0, the way you get it is you take that number times the number before factorial. So like if I wanted to find 5 factorial, I take 5 times whatever 4 factorial is. That ends up being 5 times 24, which is 120. You can do factorials on calculators, although honestly on a graphing calculator, it's a bit of a chore to find it. What you have to do a factorial on a graphing calculator is you go into the math menu on your calculator. That's over at the left-hand side. You want to go into the math menu, and once you're there, you select probability. This is actually exactly where I go when I play bingo at Christmas and find random numbers. In that probability menu, one of the choices looks like exclamation point, and that means factorial. We often use factorials to figure out how many ways things can happen. And I've got a problem here that says, suppose there's 12 people in a class. If I choose a different student to do prayer each day, how many ways could you do that? Well, what that's going to be is 12 factorial. And you could literally take 12 times 11 times 10, etc., all the way down to 1. Or you could haul out the calculator and do 12 exclamation point, 12 factorial. And you can see that you get a pretty large number. 479,001,600 would end up being the answer that we have for 12 factorial. So we'll go well past the number of days in the school year before we've exhausted all the different possible orders there are of doing that. One of the things that you're going to be asked to do in assignments is to simplify expressions that have factorials in them. Like, for example, 7 factorial over 3 factorial. It's very easy to do that on a calculator. You could just literally type that in, and it tells us the answer is 840. But it's actually almost easier to do just thinking through what factorials mean. Because it turns out that 7 factorial, of course, is 7 times 6 times 5 times 4 times 3 times 2 times 1. And 3 factorial is 3 times 2 times 1. Well, all of that stuff at the end, 3, 2, and 1, just cancel because it's all multiplication, and so you can just get rid of it. What's left is the beginning part of the top, 7 times 6 times 5 times 4, and that's really where that 840 comes from. Again, you can just think, what does this mean? Cancel the part that cancels and just multiply what's left. That's actually what you have to do when you have larger numbers involved. If you try and do on a calculator 97 factorial divided by 93 factorial, it's going to give you an error. It'll say this is an overflow error, which means you're trying to deal with numbers that are bigger than your calculator is designed to handle. It turns out that calculators typically will store any number up to 10 to the 99th power. But if you try and do anything bigger than 69 factorial, it's going to be too big. 69 factorial, you can see, ends up involving 10 to the 98th power. And if you do go into 99, or if you go over 100, 10 to the 100th power, it's going to be too big. If you try to do like 70 factorial, you'll end up getting an error because it's bigger than what your calculator can handle. And like 93 factorial is way too big. So what you've got to do instead is, again, think about, what does this mean? 97 factorial means I take all of the natural numbers from 97 down to 1 and I multiply all of them. 93 factorial is like 93 times 92 times 91, etc. Well, what's going to happen is, just like before, an awful lot of that stuff cancels. Everything from 93 on down is going to cancel. And what's left is just four numbers that have to be multiplied together. I still get a big number, but it's not so huge that my calculator can't cancel it or can't work out what the answer actually is. We get like 83 million and some change for our final answer on this. So you might want to take a minute and maybe pause the video and see if you can do 150 factorial divided by 148 factorial. And if you do that, what's going to happen is you'll have just 150 times 149, and you get a relatively small answer, 22,350. Very common thing you use factorials for is figuring out how many ways things can be rearranged. For example, I might ask you how many ways you could rearrange the letters in the word Iowa, like IOWA. I could switch that around so it said maybe WOIA. It's not an actual English word, but it is a rearrangement of those same letters. And you can kind of picture there'd be a bunch of different ways that you could do that. Well, it turns out that what that is 4 factorial, because there's 4 letters that could go first, there's 3 letters that could go second once I've chosen the first one. After those 2, there's only 2 that are left to go in the third position. And once you've picked the first 3, there's just 1 letter left over to go last. That's why it ends up being 4 times 3 times 2 times 1, or 4 factorial. And similarly, if you wanted to figure out how you're going to rearrange the letters in the word world, it would end up being 5 factorial, or 120. And you could have like any word where all the letters are different, rearrange them. It's just however many letters there are, factorial. There's also questions like, if you had 5 people sitting in a row of desks, how many arrangements could there be? That would also be 5 factorial. There is, however, a little bit different kind of question that you can sometimes be asked too, which looks like this. It says, how many ways could you rearrange the letters in the word area and be able to tell those results apart? It's what we call distinguishable permutations. And the thing that makes this different from the other examples is this time there's 2 different A's that come up in the same word. So I could, for instance, think about, switching around like the first and last letter. The problem is that's not a distinguishable permutation. I made it stand out here by changing the color of the letters, but just thinking of them as the letter A, I don't know which A is which when I do that. I can't tell them apart. However, if I switch like the A at the beginning and the R right after it, that would be a distinguishable permutation. And so what I want to know is how many permutations there are that don't just change around those A's, they actually change around letters that I can tell apart. And it turns out that what I do to find that is I divide some factorials. I take 4 factorial because there's 4 letters altogether. And then I divide that by 2 factorial because there's 2 repeats that I couldn't tell apart if I shifted. And so I take 4 factorial over 2 factorial, which, when you simplify it, is just 12 for the final answer. You could do a similar problem with one like this, where I have how many ways can I shuffle around the word advantage. Again, what I've got to do is think about how many letters are there altogether, and what do I have for repeats. And in this problem, that's going to be 9 letters altogether, and there's 3 A's that repeat. Again, on my calculator, I could just divide the factorials, or I could realize that's 9 times 8 times 7 times 6 times 5 times 4, and find out what you get for your final answer. It's going to be 60,480. Now, if you look at a word like Garrigan, the thing that's different about this word compared to area or advantage is that this time there's more than one thing that repeats. We have some G's that repeat, we have some A's that repeat, and we have some R's that repeat. And I want to make sure that I can tell things apart with all of those. So here's what I actually do. I start with how many letters there are altogether, and I do that number factorial, 8 factorial. And then I look at each of the repeats. And every time there's a repeat, I divide by that number factorial. So, like, divided by 2 factorial for the G's, divided by another 2 factorial for the A's, and divided by another 2 factorial for the R's that repeat. This does end up being 8 factorial divided by 2 factorial divided by 2 factorial divided by 2 factorial. It actually turns out that you're going to end up getting 5,040 for the answer. The screen capture you have is right there. The 4 times 3 is not right. That I actually copied from a previous problem when I made the PowerPoint, and that's wrong, but it does end up being 5,040. The easiest way to do this is literally just to divide 3 times on your calculator and see what you end up getting, and it is 5,040.